Hello everyone, welcome back to the course on Instrumentation and Process Control. Myself, Nidhi Mehta, Assistant Professor at Chemical Engineering Department, LJIET Institute of Engineering and Technology. Hello everyone, welcome back to the course on Instrumentation and Process Control. Myself, Nidhi Mehta, Assistant Professor at Chemical Engineering Department, LJIET Institute of Engineering and Technology. So, let's just start our today's session, which is Laplace transform. So, in IPC, we must know some basics of Laplace transform because it is quite essential to transform a physical function into time domain, right? So, let's start with definition of Laplace transform. So, how we can define a Laplace transform? Suppose f is a real or complex valued function of variable t which is greater than 0. Then s is a real or complex parameter. So, this is how we can define our Laplace transform. So, f of s can be written as Laplace of f of t, right? So, if I need to transform my time domain function to Laplace domain, I need to do Laplace of f of t. This can again be written as integration of 0 to infinite e raised to minus st ft dt. This is the basic formula which is used to define a Laplace transform. Now, here ft must be a piecewise continuous, which means that it must be single valued, but it can have a finite number of isolated discontinuities for all the values of t which is greater than 0, right? So, this is quite important for existence of Laplace, and another parameter which is essential for existence of Laplace is f of t must be an exponential order, which means that f of t must remain less than m e raised to minus at as t approaches to infinite. So, these two things has to fulfill for existence of Laplace. Now, let's just discuss some important simple functions for Laplace transform. First function which we will be considering is step function. So, in case of step function, as you can see here, f of t is equals to 0 to 1, that is f of t is equals to 0 when t is less than 0 and f of t equals to 1 when t is greater than 0. So, this is a step function. So, this is important function and is also known as unit step function. So, if I need to write u of t, and u of t refers to unit step function. Unit step function is denoted as u of t. So, if I need to write u of t, it can be written as Laplace of u of t is equals to 1 by s, right? So, this is the case for step function and Laplace transform of step function. Suppose we are having a magnitude a, then it can be written as a by s. The second function for Laplace transform, which is quite essential to know, is exponential function. So, as you can see that f of t is equals to 0 for all the values of t less than 0, and f of t here, as you can see, is equals to e raised to minus at for all the values of t greater than 0. It can also be written as u of t, that is unit step function, into e raised to minus at. So once you take Laplace of this particular function, what will happen? So I am taking this Laplace of u of t e raised to minus at. This is equals to 0 to infinite e raised to minus s plus a of t dt, right? Because Laplace transform of any function can be written as 0 to infinite f of t dt. So my function f of t can be written as ut e raised to minus at. So I am writing the same thing here, right? So now once you do the integration, it can be written as minus 1 upon s plus a e raised to minus s plus a of t. Putting the limits, it will be 1 upon s plus a. The third function, which is quite essential to know, is sine function. So f of t is 0 for all the values of t less than 0, and f of t is equals to sine kt for all the values of t greater than 0. Again in the same way ut sine kt, because this is step function into sine of kt. Put the values in the given formula and take the Laplace, you will be getting the value as k upon s square plus k square. So Laplace of sine function is k upon s square plus k square. Now coming to transform of derivative. How can we determine transform of given derivative? Suppose the given form is in d raised to n f upon dt raised to n, right? This is the order of equation which is being provided to us, nth order equation. If I need to write or do transform of nth order given equation, then it can be written as Laplace of nth order differential equation can be written as s raised to n, that is power which is equivalent to the given order of reaction. So s raised to n f of s minus s raised to n minus 1. Now you will simply reduce the power of s, right? So s raised to n minus 1 f of 0 minus s raised to n minus 2 f raised to 1 0 and so on until the power of s is 0, that is anything raised to 0 is 1. So here the power of s is 0, therefore it is termed as 1 and f raised to n minus 1. So once you simplify it, you will be getting the values as f of s minus f of 0. Let's solve one example based on that. The given problem is find the Laplace transform of function xt that satisfies differential equation and initial condition. So this is the given differential equation: d cube x upon dt cube plus 4 d square x upon dt square plus 5 dx by dt plus 2x equals to 2. And initial conditions are given as x0 equals to dx0 by dt, which is equals to d square x0 upon dt square. Again it is equals to 0. So we first need to determine the transform, right? So step number 1 will be determining the transform. So d cube x upon dt cube can be written as s cube x of s minus, now you need to reduce the power of s. So next power will be 3 minus 1. So it will be s square x0 minus s x dash 0 minus x double dash 0. Here s 3 minus, here s will be 0 because s 1 minus 1 will be 0. So this is the transform of d cube x upon dt cube. Similarly, we will write for d square x upon dt square and dx by dt. The transform of x can be written as x of s, and here in the front side 2 can be written, 2 is unit. So Laplace transform of unit function is 1 by s. So it will be 2 by s. Simply put the values of initial condition x0 dx 0 by dt and d square x 0 by dt here. So the term 1, this term, this one, and from here this and this will be eliminated. Right. So this is how you can simply solve this particular numerical. Now let's solve another numerical, and this numerical, as you can see here, is the numerical is solve dx by dt plus x equals to 1, given that x0 equals to 0. So first we will be applying Laplace. So once you apply Laplace, this is a first order system. So total number of terms will be 2. Dx by dt can be written as x of s plus x of s equals to 1 by s. Shift the term, take x of s common from here, so you will be getting s plus 1. So I have taken x of s common and shifted the term, so it will be 1 by s into s plus 1. Now apply partial fraction, so it will be a by s plus b upon s plus 1. Find the value of constant a and b. So for finding it, we simply multiply it and determine the value of constant. So putting s equals to 0, we can determine the value a equals to 1. Similarly, determining value of b, it will be coming b equals to minus 1. Putting value of a and b in this particular equation, right? So once you put that in that equation and take its inverse, it will be in the form of 1 minus e raised to minus t. So this is our second example. Now this is the table which represents some basics function and its Laplace transform. So 1, Laplace transform of 1 is 1 by s, t is 1 upon s square, t raised to n is n factorial upon s raised to n plus 1, and so on. Now let's talk about inverse of Laplace transform. In order to apply Laplace transform to any physical problem, it is quite necessary to understand and to involve inverse of Laplace transform. So inverse of Laplace transform can be determined as L inverse of Laplace transform, or L inverse of Laplace function can be written as f of t. So L inverse of f of s is equals to f of t. So it is simply conversion of complex domain into time domain. Inverse of Laplace transform. Now we all know that to involve Laplace transform or to implement Laplace transform to some physical problem, it is quite necessary to involve inverse of Laplace transform. So this is the formula which is used to determine inverse of Laplace transform. L inverse is given by, L inverse can be determined as L inverse of Laplace function, that is f of s is equals to f of t. If you determine inverse of Laplace function, then it is f of t. So we are simply converting from complex domain, that is frequency domain, to the time domain. Now let's discuss final value theorem. Final value theorem and initial value theorem are two important theorems which deals with Laplace, right? So final value theorem states that if f of s is a Laplace transform of f of t, then limit t tends to infinite f of t is equals to limit s tends to 0 as f of s. So now let's just prove it. So from here, Laplace transform of a derivative, this is the formula we know, right? Laplace transform can be written as 0 to infinite df by dt e raised to minus st into dt. This is equals to s f of s minus f of 0. Now, simply putting the limit s tends to 0, integration 0 to infinite df by dt e raised to minus st into dt. So, can we simply interchange the limits? So, simply interchanging the limit, it can be written as integration of 0 to infinite df by dt into dt, which is equals to limit s tends to 0 as f of s minus f of 0. So, now limit t tends to infinite, this can be written as f of t minus f of 0. This is again equals to here limit s tends to 0 as f of s minus f of 0. So, this is ultimately the statement of theorem which we have proved, right. So, this is our final value theorem. Coming to initial value theorem. Initial value theorem states that limit t tends to 0 f of t is equals to limit s tends to infinite s f of s. The condition on this theorem are not so stringent and those for the previous one, because function of interest to us, the order of integration and limiting process need to be interchanged, right. And after that we have some inverse Laplace transform. So, this is table which shows inverse function of some Laplace. Hope all the things which we have covered today is quite clear. Thank you.